Hi everybody, I'm going to do some videos on integration. The reason for that is because I've had a request for some help with integration, just because someone's missing school. I know we were doing integration just before we left, and so if you have missed any lessons from integration, or you didn't have a chance to talk to your teachers before you left, or you just finding it difficult, maybe some of these videos might be of some use to you. And yeah, if you found it difficult, maybe a different teacher saying it with a different slant sometimes helps to understand it a bit better. So I'll do these over the next few days. You don't have to do the work from these at all. They're just here just for you, if you need some help with it. Okay, so integration. Integration's really interesting. It's part of calculus, just like differentiation is. Differentiation is all to do with gradients. Integration is all to do with areas. So just to get going with integration, I'm going to do 3 graphs, and what I want you to do is try and work out the area underneath the graph. So actually I'll pause the video, draw them, and I'll play again then. Okay, so here's the 3 graphs I've got, and what I'd like you guys to do is try and work out what the area underneath each of these graphs is in terms of this big capital X. So this line, for instance, is y equals x. I'm saying this is 0, the origin. This is capital X, so this distance is x. Because you know what the graph is, you can know what this distance is as well. So I'd like you to work out what this area is. And then I'd like you to have a look at this one. Try and work out this area. You can do it as a trapezium or as a... you'll probably find it easiest to do in terms of a rectangle and a triangle. This one also, in terms of rectangle and triangle, the easiest for what we're trying to do here. Try and work out the area again between 0 and x. So just this bit, the area between the x-axis, the y-axis, the line, and this line here. So can you have a quick go at that, please? Try and work out all of those. Pause the video and then come back to me. Okay, so hopefully looking at these, you've said that this side length here is capital X, this side length here is capital X. It's a triangle, base times height is x squared, half it. So here we've got x squared over 2. For this one, this base here is x, that's x. This length here is x, and this length here is 2. So we get x squared over 2 for the triangle, and this bottom rectangle here is 2x. And last but not least, if I do the same thing here across there, that's 1, that's x, this is 3x. And so I've got 3x squared over 2 for the triangle. In here I've just got an x. So, writing all those down, for the first one I had the line y equals x. And for some arbitrary point x along the x-axis, I found out that the area underneath the graph was x squared over 2. For the second one, I had the line y equals x plus 2, and for some arbitrary length along the x-axis, I found that I had x squared over 2 plus 2x. And for the last one, I had y is equal to 3x plus 1, and then I found that the area was 3x squared over 2 plus just 1x. Okay, so what I want you to do is just pause the video, but have a look at these. What's the link between all of these? I've done something to the powers, and I've done some division every time to get from this to this, this to this, this to this. I'd like to have a think about what it is and how does it relate to differentiation. Okay, so hopefully with this one you've looked at it and said, okay, well the power has gone up by 1, and then you've divided by the new power. And with this one, that's risen by 1, divided by it, and then this has got it's had an x on it, so the this would be 2x to the 0, so the power's risen by 1 divided by 1. And this one too, 3x, I've risen the power by 1 and then divided by it. And this one was just an x to the 0, so I've risen it by 1 power and divided by it. So in other words, with what we've done here, we seem to be raising the power and dividing by the power. And if you remember with differentiation, you do the opposite of this. You bring the power down and multiply by it, and then you reduce the power by 1. So this idea of what we've done so far, this idea of finding these areas, and remember what I... 1 second, I just need to pause the video. Where was I? So this idea of integration is talking about area under a curve. So these are the areas under a curve we've found. And to find the area under a curve between 0 and some arbitrary point x, integrating seems to do the job pretty... doing this idea of reverse differentiation, raising the power and dividing by the power, seems to do the job rather well. So we're not going to do any more with area just for now, but this is just more of an idea of trying to show you that this is where this stuff comes from. We'll formalise this a bit more in the next video. But essentially what we're trying to say is differentiation and integration are the opposite of each other. So if I differentiate something and then integrate it, I should get what I started with. There's a little caveat to that one, but we'll worry about that in a moment. But the thing which you really need to take from this is that the integral, this is what the big sign for integral is, you know, dy dx tells you about differentiation. The integral of x to the n dx, this dx thing is something which needs to be on the end of the integral. Basically we're saying I'm going to integrate this thing with respect to x. Remember when we differentiate, we say we're differentiating y with respect to x. Differentiating y with respect to x. Integrating this with respect to x. So that's where the link between the what's the word I'm looking for? I can't think what the word I'm looking for is. It doesn't matter, but that's why these things are. So I'm integrating x to the n dx. That is equal to x to the n plus 1. Remember, I have to raise the power and then I have to divide by my new power. Okay, I've raised it and I divide by the new power. It's the opposite of integration. And there is a slight constant that has to be on the end as well. We'll come back to that in a moment, why this constant is here. In fact, we won't come back to that today. We'll leave that for now and come back to that another day. Just accept for now, when you integrate something, you raise the power, divide by the new power, and then you have to put a plus c on the end for some unknown reason. Okay, there's some rules of integration which are useful. So if I had a times x to the n, where a is just some number, some constant, that is the same as if I brought the a outside and did the integration of the other bit. Similarly, if I have two functions, so let's say I have the integral of f of x plus g of x, so that could be any functions that you fancy, and I was integrating both of those summed together, it's the same as integrating the first one plus the integral of the second. And these three rules between them pretty much can get you through the first two exercises into the integration chapter. So what I'm going to do is I'm just going to do an example which uses all three of these things. Am I going to do that? Yeah, I am. Yeah, I am. Okay, so let me just write that out and then we'll start playing again. So if I want to integrate x cubed bracket x plus 2 over x with respect to x, the first thing to do with these is to try and get rid of any of these products. The products make things more difficult. If we can have three different functions here, as a sum, sorry, if we can have a load of functions as a sum, then we can integrate these relatively easily. So let's get rid of this product, and to do that we'll expand the brackets out. We'll get x to the 4 plus times that by that, I'm going to get 2x squared all dx. Okay, so I've got rid of the product. I'm now going to use rule 3. I know that if I have the sum of two functions, I've got x to the 4 and 2x squared. If I've got the sum of two functions, that's the same as integrating them separately. And looking at this second one, that is the same as if I've got a constant times my x squared, so that's the same as taking the 2 outside and doing the integral. So once I've done this, I've got this down into the most easy way ever to integrate. Okay, I've only got really simple things inside. So I've got x to the 5, so I raise the power, divide by the power, plus, let's give it a constant, let's call it c1. And then I've got this one here, I've got 2 lots of this, well that's 2 times raise the power, divide by the power, and let's call this constant c2. So that's x to the 5 over 5 plus 2x cubed over 3 plus c1 plus c2. Now if we do this sort of thing where we get a couple of terms and we do a couple of integrals, we get a couple of constants, and it's just not really necessary to write all those constants out separately. You can miss this line out, you don't need to do this in future. It's easier just to not write those constants out, do the integrals, and then say, okay, I get a load of constants out, and I'm going to say that constant plus constants actually just c. Okay, it's still a constant, it's just 2 constants added together, which is absolutely fine. Okay, so at this stage, you can do a little bit of, is it 15? I think it's 15, no it's 13. So you can do some of 13a, however it's just a bit of differentiation and just trying to get your head back in the differentiation game. I would have a go at some of exercise 13b. Unfortunately I'm reading this off a computer and it's really slow. Oh, I can't get it in the right place. That looks like 13b. I would have a go at the first few questions and then get stuck into 10 onwards. So maybe question 1 to 3 and then do question 10 to 14. And if you've got any issues with that, give me an email and I can get back to you with that, and I will do some more stuff tomorrow. Okay. Thank you very much, and I'll see you again soon. Bye-bye.